So hello, and welcome to my second lecture on the chapter 5. So here I will be mainly speaking about absorption processes, spontaneous emission processes, and stimulated emission processes, and the main things that we should understand about them in order to understand what happens in a piece of a material when we shine light into it, or how on earth this piece of material can actually emit light. So these will be the main things that I will be speaking to you in this lecture. And I will now actually get started. That was my record short introduction. And now I will be mumbling to other things before I actually get started. No, I will really be starting quickly. I want to do this lecture in 20 minutes. So what happens is that we already mentioned in the kind of energy schematic of previous lecture, when the incident frequency or incident lines frequency omega is right, so when it's in resonance with the material system, then we can actually have an electronic excitation. So when incident frequency omega is close to some of the resonance frequencies, so omega Ig is associated with the substance. So this is a resonance that is associated with some electrons present in the solid piece of a material. Of course, it can be a gas, but nevertheless a piece of a matter. So then something may happen. And what can happen is that this incident photon can be actually absorbed. And quantum mechanically, and of course this is what always happens under the hood of classical physics, is that these processes always do a first approximation happen with a single photon at a time. So of course we can have nonlinear optical processes and also nonlinear processes with electronic transitions, but most of the time we do not need to deal with them. They are quite weak and do not really start playing a role before we start having strong intensity in our incident light. So we can just forget that. So we only need to think of a picture where these absorption processes happen one photon at a time. So one photon comes into the system and it excites a single electron at a time. And these processes, we can repeat them in our minds so that then we can understand that millions of electrons almost simultaneously are being excited. But nevertheless, like most of the time, the electrons do not get excited by 2 or 3 quanta simultaneously. So this is the kind of usual approximation we do in optics. And the difference between linear optics and nonlinear optics essentially is this. But let's not go there. We can do that on a follow-up course on nonlinear optics. So a photon raises one electron up in the matter, and the electronic state now is being labeled with the ket of I. So from a ground state, we go up with the electron. And in the figure, what happens is that we have an photon and it oscillates at the frequency of omega, and that is being absorbed. And what the absorption process means, that it raises an electron to the state of ket of 1, and this has been schematically shown in the figure. So we have those black circles or black dots there. So these correspond to electrons, individual electrons, and here I'm trying to highlight the fact that we actually have many electrons in our system, and most of the time also many electrons in the ground state. And then one of these guys gets excited into an upper state, into an upper electronic state, and then this energy difference here corresponds to the frequency of photon. And then, since we're speaking of electronic transitions and optical wavelengths, the energy difference will be of the order of few electron volts, of course correspond to frequencies of visible light. So the change in the energy between the states, and this is the energy associated with the incident photon, as well as the energy associated with the electron at the end of the absorption process. So that the EI is let me rephrase. So this change in energy, of course, corresponds to the energy of the incident photon, and then this EI corresponds to the energy of my electron at the end of the absorption process. And then, of course, the difference is E1 minus EG, where EG is the ground state energy. And most of the time, we can just rescale our states, energy states in the matter. so that we can say that this Eg is 0, and then this difference in energies also corresponds to the actual energy of the state. So this is what I was thinking when I started speaking. So that we can scale things out so that most of the time the Eg can be said that it's 0. And then we can calculate the frequency omega by just dividing the energy difference with the reduced Planck constant, and that gives my omega 1. And a very familiar equation to us already. What happens then, and we should think of the dynamics, is that then the electron on the excited state, it doesn't reside there forever, but rather it is associated with a lifetime tau. And what dictates this lifetime? Well, it depends on the many factors, and many of those, or essentially all of those, are beyond our scope and fall under the scope of the solid state physics. So that this is not what we're interested about. But essentially, it is the wave function, how the wave function looks like, and what are the properties of the electron. So what is its spin, in what kind of state it is, and then what kind of states it has nearby. So how easily this wave function can relax or be excited into another state. So this is essentially what dictates the lifetime. If the electron cannot easily be excited and de-excited into another state, then the lifetime is high. But if it can easily, very readily de-excite into another state, then the lifetime will be short. And essentially, if we would be thinking about the mathematics, and let's do that, we should think about the quantum mechanics of things. So we should really know what kind of wave function is associated with the electron, and then we should calculate some kind of overlap integrals between two different wave functions, so that we would know how readily the wave function can be de-excited or excited into another state. So we should be looking into the quantum mechanics. But like I said, that's not our course. Our course is on optics. But if you're interested, you can have a look on the solid state physics of the kind of relevant mathematics. But maybe here I could say that please, if you're thinking want to get some kind of rule of thumb, what kind of differences in the lifetimes we may have. Well, I guess everybody knows process of phosphorescence. So some pieces of matter can actually glow in dark for a quite long time, so that the lifetimes of those states are of the order of milliseconds, or can be up to milliseconds. And then we can see the difference in lifetimes with normal transitions, where the lifetime is of the order of nanoseconds. And that kind of transitions we don't really easily see when we put a object into a dark, so that the lifetime is so short that when we excite the piece of a matter, those states are really being excited before we start noticing that it's actually lasting. It's not an instantaneous process. But in the process of phosphorus molecules and phosphorescence, then we really can see these dynamics of the system. We excite system, and then after a long time, the system then starts being de-excited back into the ground state. And that we see as a kind of green glowing objects. So when a round of time has passed, so when in a kind of instance of time of the order of the lifetime tau has passed, then what the electron can do is that essentially it can relax into another lower energy state. And here I'm using terminology that this lower energy state is Ketov 2. And here in terms of dynamics, the relaxation factor gamma 1,2, which is the inverse of the associated lifetime, is my relaxation factor that gives me the kind of speed of this relaxation process. And graphically, in this picture, what I'm trying to say is that I can draw an arrow between the electron state in here in the Ket1, and then if I'm interested in knowing how quickly and how strongly the electron will be excited into the state 2, if I know gamma, the relaxation factor, how readily this electron relaxes, then I can calculate things via simple dynamic equations. So I just form rate equations, simple differential equations to describe the dynamics of my electron, and then I can calculate how probable it is that the process takes place, for example, in a 1 nanosecond of time interval. This relaxation takes place via a single process, and when this happens, so when it is really a single process, we speak of a radiative processes. So then all the energy that is associated with the energy difference, so essentially the energy difference between the state 1 and state 2, all of this will be associated with the emitted photon. And this is the case when the relaxation takes place in just a single process. But it could also happen via many steps of processes, and then the outcoming photons would not be associated with this large energy difference, but rather a small portions of the energy. But here, let's describe radiative processes first. So what happens is that the photon is being emitted, and in practice this takes place either at the visible, IR, or near infrared frequencies. And when several processes take place via the relaxation of the electron, then we speak of non-radiative processes. And now you can see why we are speaking of radiative versus non-radiative, is that here, even though in the end it's always all of these processes, these many processes that form up the kind of effective relaxation, even though in each of these individual processes a photon is being emitted, there's actually many of these processes, so that the energy difference between the state 1 and 2 is not associated with a single photon, but let's say it could be, for example, 10 photons, so that then the energy is being more of thermal in nature, so associated with very long wavelengths, than rather a kind of short wavelength associated, for example, with visible light or near infrared. So phonons essentially are being created into the material. Phonons are lattice vibrations and quantized lattice vibrations, so that they then essentially this is what happens. So that kind of processes we're speaking of. And what this means in practice, that if we have phonons inside the material, essentially macroscopically, that means that the piece of a material is being heated up in temperature. And of course, these phonons, they're also associated with possibilities that they will also emit light. Sorry, not light, but electromagnetic radiation. They will emit thermal radiation, so that they of course, it's not just the fact that the energy is being associated with the electrons and the atomic oscillations in the solid piece of matter, but also there is this radiation part in the energy distribution. Then let's look what kind of other processes may happen, and then after a passing of time again of the order of the relaxation time, then the electron can also relax to the ground state G, and then when that takes place, we emit a photon, and then the frequency corresponds to the energy difference between the state 2 and the ground state. So we just, instead of distinguishing the actual process that we de-excite from the state 2 into the ground state, many times we just label these as with the 2, so that that will be the kind of transition from the second excited state. This process, as the others, is known as spontaneous, and when it is spontaneous, we speak of spontaneous emission. So please look at the energy scheme. So we have electron in here in state, and it is being relaxed into the ground state, and the energy difference essentially corresponds to the frequency of light. And when we are speaking of generation of light, then the energy difference is of the order of electron volts, so that then the frequency of our photon actually corresponds to visible light and not, for example, far infrared radiation. That would be the case if the energy difference would be very small. And when this process takes place spontaneously, so it would be just like a stochastic process in nature, then we would be speaking of spontaneous emission. And in practice, since we're speaking of atomic emitters here, fluorescent molecules, quantum dots, they're very small. So in practice, this emission takes place from a very small volume. So that the volume, if you can imagine our volume where this de-excitation takes place, we can think of that as a cubic volume, L cubed. Then each side lengths of this cube are way smaller than the frequency of outcoming radiation. And this implies to us mathematically, and this is related to the wave equation, so that the properties of the Maxwell's equation. So then we can really reasonably describe that the emitted photons, emitted electromagnetic radiation can be very well described as a dipolar source. So this is what we know from mathematics. So essentially we put a tiny source term into the wave equation, and then we solve the system, the differential equation, that what kind of wave corresponds to a tiny point-like emitter. And then that gives me the electric dipole radiation pattern. And that we can use here most of the time. So what happens in these spontaneous processes? They're actually being driven by vacuum fluctuations, so that the initial phase then of these emitting photons will be randomized. So this is what happens in spontaneous emission processes. So even though we can be exciting our system with a laser, and even though all of these states, they are associated with electrons oscillating, and since it's a given frequency, of course, they oscillate roughly at the same frequency, then ultimately, when this process takes place, it's being seeded by a vacuum fluctuation. And since the phase of the vacuum fluctuation is random, then also the output photon phase is randomized. And this is the key to understand what happens in spontaneous emission and spontaneous processes and versus stimulated emission processes. So this is very important to note here. Spontaneous emission, the phase of my output photon is randomized. And what can also happen, this is the final process of interest, is that the emitter, our electron, can also interact with a photon. And now if the photon oscillates close to the resonance frequency, omega 2, then it is that this photon can cause a relaxation of the electron state. And if that takes place, then we speak of a stimulated emission. Of course, quantum mechanically, like if you would do the math, this is exactly the same kind of calculation that we would do with the vacuum photon, vacuum fluctuation. But now the key here is that we can actually, we could pump the system with a bunch of photons. And since we could then increase the number of photons here, there are regimes when we can actually increase the strength of stimulated emission quite high. And since we are pumping the photons, we can also decide that what is the phase of these photons. And then it's this phase that can then gets transferred into the output photons, kind of being emitted by the material system. So here, the key things to remember with stimulated emission processes is that the phases, the wave vectors, so essentially the directions in which the photons are being emitted, and the other properties of photons. Here I'm mainly thinking about the spin of the photon. They correlate with each other. And correlation means that there's a mathematical relation between the two different wave functions, and this is really key in many of the applications. So essentially all emitted photons, we can understand that they have the same k, so the same wave vector, so that they are very highly directional. They have the same phase, so that they amplify each other, so that when we are summing these waves together, they constructively interfere, and this amplifies the intensity of light, and then the polarization will be the same, so that they kind of oscillate in the same way than the other incident photons that are being used to seed the process. And here, what can happen is that the process can amplify incident light. So this is schematically shown in here, so that I have my incident radiation, this one blue wiggle here, that's my incident photon. And then this single photon may stimulate the emission process. Emission process here, and then 2 photons are being created. And I'm trying to highlight here that I'm actually having same kind of photons here, so that it's their phases that are correlated. It's their wave vectors that are correlated so that they go into the same direction, and also the polarization is being correlated. And essentially what that means is that we are amplifying light. So we could also think that this would be our signal, our piece of light we want to amplify. And here the material system, the electrons are now being used to amplify this portion of light. So this is also what we could think of these processes and how they could be useful. So light interacts with matter, and that takes place also in situations when the frequency omega of the photon is very far from the resonance frequency of the matter, so omega IGs, or in general omega IJs, because we could also excite an electron from upper state into yet another upper state. And this can take place. So we do not always need to have a be or be close to the resonance frequency. And when this is the case, photons are not being absorbed, but rather they are being scattered by the material. And the rule of thumb here is that when the incident frequency omega is different from the resonance frequencies of the matter, then scattering processes are actually the processes of main interest. So this is what happens. We have a atomic system, and we have electrons in there, and when the frequency of incident light is different, then instead of absorption, so of being exciting the electron into an upper state, some interaction takes place, and then the photon is being scattered via this atomic emitter. And if we are looking of how we could describe this mathematically on the microscopic picture, the incident electric field essentially displaces the electron from its equilibrium. So that is just a simple dynamics that we can try to develop with the mathematics, and then it creates a dipole moment into the material. And then once we know the dipole moment, we can plug that and calculate the material polarization, and then we know how light is being emitted or being changed due to the fact that we have matter that is interacting with our piece of light. So material polarization that has been created, it modifies the propagation of light. So one way of understanding these things would also be the case that on a macroscopic Maxwell's equations, we did have the material permittivities there, and that gave rise to the refractive index profile of the material. So in a way here, we can understand that the microscopic picture, we have the scattering processes when we are not close to resonance frequencies of the matter, and these scattering processes effectively give rise to slowdown of incident light. And that slowing down on a macroscopic scale is being described using the refractive index. And then the final slide. Okay, when we have phases of the incident photons in these scattering processes, the phases are being correlated with the scattered photons' phases. So here's a phase correlation between the incident light and the scattered light, and this is also very important in terms of applications and understanding physics in scattering processes. Far away from resonances, the phases essentially are almost equal. More on this on the Lorentz model in the next chapter, but this is what we can already dictate and say here. So they're always almost equal, the phases. When we go closer to the resonance, then a phase difference is being created between the incident photon and the scattered photon. And of course, this will be treated in the next section. Please be warned, Lorentz model for the atom and emitter electron. This is the piece of math that we can use to understand these kind of sentences. How come this takes place? And finally, the nature and the applicability of these processes, let it be spontaneous absorption, spontaneous emission, or stimulated emission, or scattering, these are defined by this fact. Whether the phase correlation between the photons exists or does not exist. So this phase correlation really is the key in terms of applications of these processes. So correlation remains when we have scattering processes and when we have stimulated emission. And the correlation between the incident light and emitted light vanishes when we have a normal absorption and spontaneous emission processes. And this is really the key that we should appreciate when we are thinking about light sources. So essentially, I can think of a normal LED versus a laser device. And the kind of main difference in the physics that gives rise to these kind of light sources is really the correlation between the electrons. Do we have it or don't we have it? Thanks. This is all I wanted to say in this lecture. And please follow me in the next lecture where I will be actually speaking about the Lorentz model so that we really understand more of the mathematics that we can use to understand things on a quantitative picture. So thanks for your time and patience. And please join me quickly for the upcoming lecture. Thanks and bye-bye.